Okay, good morning. Today we are going to uh, talk a little more about dispersion in a prism and specifically angular deviation. So, you all know very well how triangular prism looks like. So, if I were to draw a triangular prism here, right? So, we know from Snell's law that any light falling on the prism is going to get refracted, and we know how that is going to happen. So if I have an incident ray coming here, let's say, right, this is the incident ray, I can draw a normal to the surface, right? The normal to the surface looks like that, right? So the angle, this angle is the incident angle, which is, let's call it theta 1, right? And now this ray is going to bend, right? And so you would get another angle theta prime, right? So this ray is going to bend here. So this refracted ray is theta 1 prime. Let's call that, right? And now this ray is going to translate all the way to the other side of the prism, and then it's going to come out again from the prism here. So if I were to draw another normal here, right, then I can write this angle, the angle at which the refracted ray that passed through the prism went to the other face is theta 2, and it comes out at an angle of theta 2 prime, let's say, right. So we're saying that it comes out at an angle of theta 2 prime. Okay, so now look at how the ray is in between in the prism, right? So let me use another color here. So look at this ray here. It is not flat, right? It has an elevation, right? And also, if you were to come from this side of the prism, from the right to the left, or from left to the right, or the other way, right, the way the ray goes through the prism looks different. Here it goes from theta 1, goes up, then bends down. Here it goes up, then bends down, and comes out this way, right? So what we are going to do is we're going to extend these lines first. So I'm going to just simply extend this line, and then I'm going to extend the other line as well. Right, so these blue lines that I extended are, this blue line is the extended path of what would the path have been if there was no prism in place, right? Then this angle between this line and the actual path that is inside the prism is what we call as delta 1, the deviation for the incident beam, and this is what we call as delta 2, which is the deviation for the outgoing ray. So once again, here what we are looking at is, we are looking at a prism, and we are looking at how ray deviates in the prism. So when the light enters, right, if there is no prism, or if there is no interface here, if there is no glass interface here for the prism, right, then the light ray would have gone straight like the blue line. But if there is an interface, it bends, and that angle is theta 1 prime. We know the relationship here through Snell's law. So that difference between how the ray of light would have gone without the prism versus with prism, the difference in that angle here is what we are calling as delta 1, right? That is the deviation. Same thing for the ray that is going out. we're calling it delta 2, right? So now let us call this angle of the prism as A, the top vertex, the angle as A. Now if I extend these both the normals, if I extend both these normals, they intersect here. So let me call this angle as B. Okay, so now we can write down some things that we know from Snell's law. For example, from Snell's law, we know the relationship between theta 1 and theta 2. Right, so I can write, um, if I assume that this refractive index n1 is simply 1, that is air, and I call the refractive index of this prism as n, then I can write for the incident ray, we can write Snell's law as sine theta 1, right, as sine theta 1 is equal to n sine theta 1 prime, right? So 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 that's what we can write from Snell's law. We can do the same thing for sine theta 2 prime as well, and you would get the same relationship there, right? Except I'm going to write it the other way around. That is, here I would have theta 2 prime, and this should be theta 2 prime, and this should be theta 2. So this is theta 2, this is theta 2 prime. So if I want to write the Snell's law for the outgoing beam, then that would be n sine theta 2 prime, because now the incident ray is in the refractive medium, and this should be there's no n here because it's going out into the air. So I would have then sine theta 2, sine theta 2, right? So those are from Snell's law. Now we are going to write delta 1, right, is the angle deviation for the incidence beam. So that is simply the angle of deviation is, if it did not refract, it would have continue to go at theta 1, right? But because of the refraction, it changed its angle by theta 1 prime. So the deviation for the first beam is this. Similarly, you can define a deviation for delta 2 as well. That is, it is incident at theta 2 minus theta 2 prime, right? So these are just deviations, delta 1 and delta 2, that we talked about. Now, if I look at this triangle, if I look at, let me get another color here. If I look at this triangle, the green color triangle, you see there are three angles in there, right? And so I can write the total sum of those angles as angle B, right, plus then I can write theta 1 prime and theta 2 prime as 180 degrees. So this all should be equal to 180 degrees. So then I can write B as 180 minus theta 1 prime minus theta 2 prime. So I have this equation from the green triangle that's up there. inside the prism. What we are trying to do is we are trying to achieve an expression for minimum angular deviation. That is, what should be the angles to have this deviation to be minimum. And as you will see from this angle of minimum deviation, we will derive refractive index as well. So this can actually be used as an experimental method to determine the refractive index of an unknown material, right? So we have that equation, um, b is equal to 180 minus theta 1 prime minus theta 2 prime. But now if you look at the quadrilateral, let's say, if you look at the quadrilateral, that is this, right? So this is the normal here, right? So this total angle here, this total angle, this total angle is 90 degrees. Let me draw it with another color so that you can see it more clearly. So let me use blue. So this angle between the normal and this is 90 degrees, right? So using this, I can write then this angle here, this extra angle here, as 90 minus theta 2 prime, or I can write a, this angle a, right, as a sum of theta 1 prime and theta 2 prime. Excuse me. So we can write this as theta 1 prime plus theta 2 prime, right? So from here, then I know if I know one of the angles, right, theta 1 prime and theta 2 prime, I can relate it to A, and we have how we can relate these two to B, because here we have theta 1 prime minus theta 2 prime. So I can write B as 180 minus 180 minus A. Right, that's quite simple to see actually. If you look at this quadrilateral, right, if I look at this quadrilateral, right, A is at the top, right, this in this quadrilateral, A is at the top. So angle A plus angle B plus these two other angles, whatever these angles are, right, should equal 360 degrees in a quadrilateral, right? So we know that 180 minus 360 minus 180 gives you 180. So A plus B, the opposite angles in the quadrilateral, right, should sum up to A 180 degrees. So B is simply 180 minus A. And because we have here theta 1 minus theta 2 prime, we can write A as theta 1 plus theta 2 prime. I hope you are able to see what I'm talking about here. If you are not understanding what I'm saying, I suggest that you go to section 3.3 in Pedrotti and look at the diagram, the figure of the triangle, draw it for yourself, and ensure that you are able to manipulate all these angles, right? So then I can write down a net delta as the sum of delta 1 and delta 2, right? And my goal is now to find this delta to be minimum. So this delta is equal to theta 1 plus theta 2. I'm simply adding up both the angles of deviation. So theta 2 minus theta 1 prime minus theta 2 prime. So now I have several equations. My goal is to find the angle of minimum deviation. So what I would like to do is I would like to plot a graph, right? A graph with delta on the y-axis, that is the deviation, and angle of incidence. Angle of incidence is theta 1, right? On the so theta 1 on the x-axis. Now as I change this angle of incidence, right, then theta 2 is going to change, right, because theta 1 determines theta 1 prime, and theta 1 prime then later determines theta 2 prime, because that's what decides how the rays goes inside the medium this way, right? And so all these parameters are dependent except theta 1, right? Theta 2, theta 1 prime, and theta 2 prime all are dependent on theta 1. So delta is really a function of theta 1, right? And I know how to express these theta 2, theta 1 prime, theta 2 prime in terms of other things. For example, here instead of minus theta 1 minus theta 2 prime, I could write it as minus a, right? I could write that as minus a. So then that would be basically the angle of the prism that I can measure, and I know what it is. And finally I only need theta 2, and I know how to get theta 2 from here. Theta 2 is sine inverse, right, of n sine 2 theta 2, n sine theta 2 prime. So this theta 2 prime is the angle at which the ray is coming out of the prism. So I can measure that as well. So theta 2 prime is the angle at which the ray is coming out. So I can measure this theta 2 prime. And from this equation, therefore, I can know what theta 2 is, right? So from there, I can basically plot a delta versus theta 1 graph, and there I can find what should be the angle of minimum deviation. And so if you plot it, it looks sometimes like something like this, right? So you can identify, okay, this is the angle of minimum deviation, right? So the nice thing with this angle of minimum deviation is that at angle of minimum deviation, basically what happens is your ray is flat inside the prism. So if I have a prism, um, if I have a prism and I have a ray of light that's going here, at the angle of minimum deviation, this ray inside the prism is flat. So we have a flat ray inside the prism. If you have a flat ray, it basically means that it doesn't mean that delta is zero. Delta is still not zero because the ray is refracting. So it is not the angle of minimum deviation. Don't misunderstand it to be zero. It is not zero because if I were to draw this ray going directly that way, right? So this itself becomes the angle of minimum deviation, right? The angle of refraction itself becomes the angle of minimum deviation there. So it cannot be zero. Zero means it never refracted. If angle of minimum deviation is zero, it implies that the ray never refracted, but that is not the case here, right? So the ray always refracts inside the prism because there is a change in refractive index, and for the angle of minimum deviation, the ray inside the prism is flat. And from the equations that we have looked at for delta, right, we can then write delta as basically, in this case, everything is symmetric, so incident angle is equal to the output angle. So instead of theta 1 plus theta 2, or theta 1 prime minus theta 2 prime, you get the same angle. They're all symmetric, right? Whether you go from this side to the other side or the other way around, right, it looks symmetric. Here the ray goes in, ray goes flat, ray comes out. If I go from the other side, the ray goes in, it's flat, it comes out, right? It's completely symmetric. So that's why all the angles become equal to each other, and A, which is theta 1 plus theta 2 prime, is simply now 2 theta prime, right? Or I can write theta prime as A by 2, or from here I can write delta as not delta, theta as delta plus A, right, because 2 theta prime is A, divided by 2. So theta prime is A by 2 and theta is equal to delta plus A by 2 for angle of minimum deviation, right? And we know from Snell's law that theta and theta prime should be related by Snell's law. So theta is the angle of incidence, right? So if I were to draw a normal here, this would be theta, right? Um, our Snell's law would be equal to n sine theta prime n sine theta prime. So this is the theta prime here, right? That's the refracted angle. N sine theta prime, which is inside the prism, is equal to n sine theta if the medium outside the prism is simply air. The refractive index is 1. Right now we know theta is a delta plus a by 2 and theta prime is a by 2. So I can write n as sine theta by sine theta prime, or I can write it as sine delta plus a by 2 delta plus a by 2 divided by sine a by 2. So A is the angle of the prism. So from the angle of the prism, you know what is sine A by 2. And delta, we just saw how to figure out the angle of minimum deviation, delta. We can do that by plotting delta as a function of angle of incidence like I have shown you. So you can figure out experimentally what delta is, and you know experimentally what A is, because it's just the angle of the prism. So you should be able to see what the refractive index of the material is. So we can from here we can make even a smaller approximation that for very small angles I can write sine theta as theta. So then I can write n by making another approximation, that is sine theta is almost equal to theta. I can write this as a plus delta by 2 divided by a by 2, right, almost equal to, right, so this is a plus delta whole by 2, right, so that would be equal to 1 plus delta by a, right, or I can write another expression for delta, the angle of minimum deviation, as angle of the prism times n minus 1, right. This is, we got an approximate expression for delta. So if you know, if you have the prism, you can perform the experiment, that is you can vary the angles of incidence. So after varying the angle of incidence, for example, you should be able to uh, uh, after varying the angles of incidence, you should be able to get delta, and so that's what we plotted. And if you have just the experimental parameters such as the angle of the prism and the refractive index, then we saw that we can obtain an expression for delta as a of n minus 1, right? So once again, angle of minimum deviation doesn't mean that the angle is zero. It is the deviation, it is how much the ray deviates because it enters the prism. So if it was going at an angle theta 1, and because of the refraction it had to change that angle to theta 1 prime, then the difference between the theta 1 and theta 1 prime is what we are calling as deviation. And at minimum deviation, at the minimum angular deviation, the ray goes flat inside the prism. So at the ray of when the angular deviation is minimum, the ray goes flat in the prism. So from here, from pure geometric considerations, we were able to derive an expression for either the refractive index if we know angle A, that is the angle at the top of the prism here, right? Or we can do other way around. If we know the refractive index of the prism to begin with, we can calculate what should be the delta. So this is in fact angle of minimum deviation is in fact traditionally used to determine the refractive index of glass. Of course, now we have more modern and much simpler and much different methods that can give us angle of deviation, the refractive index, right? But this is just one such method. Okay, so we'll stop here, and then in the next lecture again we'll come back to wave optics.